Hi everyone, welcome back. Today's lesson we're going to be looking at derivatives and rates of change. And to start this off, we're going to be looking at the tangent line. Now, the tangent line to the graph y, or to the function y is equal to f of x at the point P that has coordinates a comma f of a is the line through P that is going to have a slope m, which is defined by the limit as x is approaching a for the difference in f of x minus a divided by x minus a. Or equivalently, the limit as h is approaching 0 for f of x plus h all divided by f of x, for f of x plus h minus f of x all divided by h. This can also be called f prime at a. So again, notice what we have here. We have this new notation that's going to come about, and this new notation, we're calling this f prime at a. And this now talks about, as we see here, the slope of the tangent line. Okay, so it's the slope of the tangent line to the given function f at a given point. And this is how we start talking about derivatives. We first start extracting what it means to be their slope of the tangent line for that given function at a given point, in this case P. This works provided the limit exists. Now, another really nice aspect about this slope of the tangent line to a function is that we can extract this a little bit more general, or to be a little bit more concise, we can start talking about this instantaneous velocity. Now, if you remember back from section 1.4 and section 1.5, we started looking at the difference quotient and the average rate of change. And in that particular section, we also discussed instantaneous velocity. However, we didn't give it a very strict definition, whereas now we actually do get to use that definition. So follow me along to Geogebra really quick as I'll give you a demonstration of what it is that we're doing. That way we can start getting that visual, and then we can start working with this algebraically. Alright, so here we are on Geogebra. Now, what I have here on Geogebra is I have this one graph, which we'll call x cubed plus x squared minus x. And that's going to be the graph here in green that has these curves. And I have these other points listed on here. I have point A and point B. Now, you will see that point A doesn't move no matter what I do to it. So point A is fixed. However, point B is the point that is moving. And you're also going to see a numerical value here on screen, which is denoted as h. So h, as I have calculated here, is basically just the distance between the x coordinates for the point A and the point B. And you'll see here as B gets closer, that h value starts getting smaller and smaller and smaller. As the point B gets further away, then that h value starts getting larger and larger and larger. And naturally, that's the way this is going to take place. So what we want to do with this limit is we want to do what I basically did here. I want to fix a point, we'll call this point A. In the definition, we called it point P. However, let's just call this point A. Now, as I'm taking this limit, or as I'm taking these x values to get closer and closer to A, look at the slope of that line. The slope of that line, oops, that was too far. The slope of that line is actually getting closer and closer and closer to the slope of the tangent line that is given here. Now, because this line is the secant line, right? It's a secant line because it's going through point A and point B, but as we start making that secant line, or as that b value gets closer and closer and closer to point A, it now becomes a tangent line at this point. There we go. So now this becomes the slope of the tangent line. Now the slope of the tangent line is now representative of the rate of change for this function at that given point. And that's exactly what we want to do within this specific definition for the slope of a tangent line. Notice the distance, that h value, the distance is now 0. And essentially that's what we want the distance to occur when we're looking at the difference between the x values. So let's go back and let's now start looking at this more algebraically. So now when we're looking at the definition, if you look at the definition, when we're looking at the limit of the difference quotient as h is approaching 0, that's exactly what we're looking at there. We're looking at that distance, that h value. We're looking to make that 0. So we're going to say the limit as that distance is approaching 0 should get us that slope of the tangent line that we're looking at for the function f of x at the point A. And this first definition that we're looking at, or the first, let's say, formula that we're looking at, looks at the difference or the change in between the function x values and the given point A that we're going to be approaching. So regardless of which equation we're using, whether we're using an average rate of change and we're taking a limit, or whether we're using the difference quotient and we're taking the limit, regardless which one we're using, we should still wind up at the exact same answer. So on this first example, we now want to explore, or we want to find, the slope of the tangent line to the curve y is equal to x minus x to the power of 3 at the point 1, 0. Now, if you're one of the students that has seen calculus before, I will ask you to keep in mind that we are not using anything that we have not learned in this course yet. So if you happen to know, let's say, a shortcut for finding the slope of a tangent line, for these particular sections, you will not be able to use it. So let's go and let's start employing these definitions that we have so far. Now, I'm going to go through and I'm going to show you both definitions and how they both play out. Okay, so let's go with the first one, the one that I like going with first. This is going to be using the limit as h is approaching 0 for f of x plus h minus f of x all divided by h. And this will be f prime evaluated at a. Okay, so let's go ahead and let's start working with this. Now, what we're going to have here, okay, so what we're going to have here as we start working with this, and I want to make a small correction here. And so I want to make a small correction, and that small correction is going to be in the difference quotient that I just wrote. The correction is going to be, because I'm looking at f prime at a, this is going to be the a value evaluated into the function that we are working with. And that's going to go the same thing for the definition up top on your screen. It's going to say f of a, and it's going to say f of a for these values. Okay, so please make the adjustments on your notes, and from there we should be able to have it. Okay, so let's go ahead and let's start using that difference quotient. So going through this whole process, we're going to be looking at the limit as h is approaching 0, and this is going to be for f. Well, we're going to take our a value And the a value that is given to us is given by the ordered pairs. So a is equal to 0, and the second value is given by your f of a. In other words, this is f of 0, which is equal to 1. So using this input, I'm going to be using f of a plus h. So a is 0, so I'm going to keep 0 there, plus your h value. All right, so your h value, will actually just keep it as h. And then we have minus f at a, which will be f evaluated at 0, all divided by h. So again, this is the slope of the tangent line that we're looking for. And so let's go ahead and keep evaluating this, and I'm going to make my substitutions really quick. F of 0 plus h, well, that's going to be substituted into my function here. Notice that 0 plus h will just leave us h, which means we're just looking at f of h minus f of 0, all divided by h. So let's make those substitutions and let's work with that. Okay, f of h, in other words, the function evaluated at h will be h minus h cubed. That's my f of h. Minus f of 0. Well, f of 0 is just 1, so that's what I'm going to substitute in here. All divided by, well, yep, you guessed it. Okay, and as I'm looking at this, I realize, oh my goodness, I made a mistake. Now, my apologies there. It has really been a very exhausting weekend. So my sincerest apologies, everybody. I miswrote this point down. The point is 1, 0. Now it makes sense because when we evaluate, there we go, when we evaluate my function at 1, we get 1 minus 1, which is 0, which isn't the other way around as I had previously stated. Okay. So we're going to make those changes really quick. And again, my apologies. Okay, so that should just make my adjustment here. Now, making this adjustment here, again, I'm going to have f of, in this case, cheese and crackers. Let's see my a value. Oh my goodness. Okay. Let me actually just, instead of trying to make this adjustment, let's go ahead and let's start rewriting it. That'll give us the opportunity to write m. So the limit as h is approaching 0, this is going to be for my function f of a plus h, and again a is 1, so this is going to be 1 plus h, minus f at a, which is going to be f of 1, all divided by h. Now we can go through and we can make our substitutions. So my x value takes on 1 plus h, so that's 1 plus h for my first x value. Then my second x cubed value, so that second term, takes on 1 plus h quantity cubed. And again, all I'm doing is making these substitutions. 1 plus h into the first x value, 1 plus h into the second x value. And then we have minus f of 1. So the nice part about this is that f of 1 is just going to be 0. Okay, and this is all divided by h. So I'm going to highlight what we were looking at here. That in this first part, when I'm looking at f of 1 plus h, that is all of this piece right in here. And for that last piece, that minus f of 1, well, f of 1 is just 0, and that's where I'm looking at that specific value. Now all I have to do is keep on expanding, and that's exactly what I'm going to do. So I'm going to keep going and trying to take this limit, so the limit as h is approaching 0, and let's see, the first term I can't do anything, so the first term stays as is, 1 plus h. Alright, that stays as is. The second term does expand, and since it's a cube, I'm going to expand using a cube expansion. So this is naturally going to be 1 plus 3h plus 3h squared plus h cubed. And then minus 0, I don't need to denote the minus 0 there. And so all of this is then being divided by h. Now, again, one of the things that you're going to notice here is that as we distribute the minus sign, or that negative, we're going to get the limit as h is approaching 0, and we're going to get minus 1s to cancel, so they're just going to cancel out. And then we're going to be left with h minus 3h minus 3h squared minus h cubed, all divided by h. And you'll see that as long as they all have an h value, then this is going to simplify into, well, this is h minus 3h, so that's negative 2h. So this simplifies into negative 2 minus 3h minus h squared. And now if we take the limit here, well, 3h, that's going to approach 0, so this is going to be practically 0. H squared, again, it's approaching 0, so that's going to 0, which means we get an actual slope of negative 2. And this is what we're looking at. This is our f prime at a, which is 1. So, when we're asked to find the slope of the tangent line, that's exactly what we did at this point in time. We found the slope of the tangent line, and hence, we're done. That's it. No more, no less. Now, let's see what happens if we use the other method. So, using the other method, in here, I'm going to be using the limit as x is approaching a for the function f of x minus f at a, all divided by x minus a. So let's use that function. Okay, so I have my slope. This is going to be the limit as x is approaching, and my a value is 1, so x is going to be approaching 1. F of x, I don't have any substitution for f of x, just the function value itself, minus f at a, so f at a, that's going to be f of 1, all divided by x minus a value, which is 1. Okay, it's not looking too bad. Let's go ahead and let's make our substitutions then. Limit as x is approaching 1, we get f of x, which is just x minus x cubed. Okay, that's nice. And then we have f of 1. Well, f of 1 is just 0, so that's minus 0, all divided by x minus 1. Okay, looking good so far. Limit as x is approaching 1. And in my numerator now, I can factor out an x, and I will be left with, in this particular case, 1 minus x squared. Okay, looking good, divided by x minus 1. Now, look at your numerator there. Your numerator now has a difference of squares, so we can factor out that difference of squares. That's 1 minus x times 1 plus x, all divided by x minus 1. Now, you'll see that we have opposite terms on one of the factors, and hence we will be able to cancel those out, but when we cancel one of them out, because they are opposite terms, then we're going to be left with a negative value. So we're left with a negative 1. This now gives me the limit as x is approaching 1 for negative x times x plus 1. Taking the limit now, well, as limit of x approaches 1 for this polynomial, we get negative 1 multiplied by 1 plus 1, which is negative 2. And this is the exact same value that we found before, that f of f prime at 1 was equal to m, which was negative 2. And again, it doesn't matter which value or which equation you use, so long as you're using one of the equations that we are given for the slope of the tangent line. Now, as an added bonus to this question, could we then say find the equation of that tangent line? Well, the answer is yes, right? Because in order to find the equations of lines, all you need are two items. Number one, you need a slope. Number two, you need a point on the line. And in this particular case, we just found a slope, and given a point, which we have at the top of the screen, then we will be able to put these two items together and find the equation of the tangent line at a given point to this curve. So that's where it starts getting really interesting in identifying that we can build these equations of tangent lines. All we need is this whole concept of a derivative. So let's work on a second example, and we'll see where we go from there. Okay, so by some internet magic, we'll make that second example appear in just a little bit. All right, so here's the question that we're looking at for this example, where we want to find an equation of the tangent line to the curve y is equal to 2x plus 1 all divided by x plus 2 at the point 1, 1. Now again, what we're given here is we're given f of x. Okay, so we're given this function f of x. F of x is the function of 2x plus 1 all divided by x plus 2. We're given an a value. The a value is the first point in the ordered pair. That's my a is equal to 1 value. And we're also given my f of a value. So here, f of a is basically f of 1. In other words, it's also 1. So given all of these important details, we now have to use one of the equations for the slope of the tangent line. So as you look up here at the top of your screen, we either want to use the first equation, this first equation, the one that I circled, which is the limit as x is approaching a for f of x minus f of a all divided by x minus a, or we're going to be using the limit for the difference quotient, which is the limit as h is approaching 0 for f of a plus h minus f of a all divided by h. So again, we must use one or the other. And so in this particular case, it doesn't matter which one we use, okay, as we saw from before. So let's go ahead and let's work with one of them. Okay, so I want to choose here. So I want m is going to be f prime evaluated at a, which will be f prime at 1, which is equal to the limit. I'm going to say h is approaching 0, and this is going to be for f of a plus h. Remember, f of a is just 1, so that's going to be 1 plus h minus f of a all divided by h. So let's make the substitutions then. So making the substitution into my function, we now have 2 times 1 plus h plus 1 all divided by 1 plus h plus 2 minus f of 1. Well, f of 1, we already know what that is. It's just 1. And this is all divided by h. Okay, so let's keep going. Let's simplify as much as we can here. So the limit as h is approaching 0. So my numerator for my complex fraction, I'm going to distribute. And that's going to be 2 plus 2h and then plus 1. So that's going to be 2 plus 1, which is 3. So that's 3 plus 2h all divided by 2 plus 1. Then that's going to be 3 plus h. And then I have a minus 1 all divided by this constant of h. Okay, so let's keep going. Now, in order to clear this complex fraction, what I'm going to do is I'm going to multiply the big numerator by 3 plus h and the denominator as well by 3 plus h. In doing so, I now get this newfound limit as h is approaching 0 for my numerator, which will be 3 plus 2h minus this quantity multiplied, which will be 3 plus h all divided by h times 3 plus h. Okay, that's looking pretty good now. Again, the limit as h is approaching 0. So notice the 3's are going to cancel, and then the negative is going to distribute into the h. So we're left with 2h minus h, which is just h, divided by h times 3 plus h. And look at this. Simplify, simplify. Which means we're left with the limit as h is approaching 0 for 1 divided by 3 plus h. So take the limit. Taking the limit here, h is going to go to 0, which means we're left with 1 over 3. And there we are. We found the slope. So now that we found the slope, we want to return our attention to find the equation of the tangent line to this curve at that given point. So in order to find the equation of any line, the equation of any line is y minus y1 is equal to m times x minus x1. And again, we need to know the slope. Well, what's the slope of the line? Well, we found that to be 1/3. X minus x1, so x minus the point for the x coordinate for the point, which is 1, is equal to y minus y1, where y1 again is the y coordinate for that ordered pair, just 1. So we simplify here, and we get y is equal to 1/3 x minus 1/3, and then plus 1, which means that the equation of the tangent line is y is equal to 1/3 x, and then we add these two together, and we get 2/3. And there we are. Easy peasy, with a little bit of some lemon squeezy in there. Awesome. So again, if we wanted to find the slope of the tangent line using the other method, then that other method would suffice as well. Now, I want you to pay close attention to this, because on exam number 2, so again notice, exam number 2. On exam number 2, when you are going to be asked to find the derivative of, let's say, a function at a certain point using the limit definition, this is going to be one of those processes that you can show. Awesome. So, now that we have a little bit more of a warm feeling about this, let's go ahead and let's start extracting some more items. Okay, so let's go ahead and let's work on a different example. So again, you're going to see the example pop up in just a little bit here. All right, so here's the question. This question says that the displacement in feet of a particle moving in a straight line is given by s of t, which is equal to 1/2 t squared minus 6t plus 23, where t is measured in seconds. And for part A, we want to find the average velocity over each time interval. Now remember, the average velocity for a given interval, or given a function, that was using the function f of b minus f of a, all divided by b minus a, and this was your average velocity, or your average rate of change. And this was on the interval from A to B. And that's exactly what we want to do here, is we want to start calculating this average velocity, or in other words, the average rate of change. So in this particular case, when we have the average rate of change, so the average rate of change for this given interval, we're going to have the function s of 8 minus s of 4, all divided by 8 minus 4. Now, making in the substitutions, s of 8, well, if you make the substitution for s of 8, you're going to find that that's going to evaluate to 7. If you make the substitution for s of 4, so make the substitution where t is equal to 4, once again you're going to find that the answer is 7. So you get 7 minus 7 divided by that denominator, 8 minus 4, which is just 4, And in this case, 7 minus 7 is 0, so we just get 0. So the average rate of change, or in this particular case, the average velocity in this time interval is 0. Okay, so let's look at the second one. Again, I'm looking for my average rate of change. In this particular case, I'm going to take my function s of 8 minus s of 6 divided by 8 minus 6. Well, let's make our substitution. S of 8, substitute the value of 8 into your t values, and s of 8 we should get, again, 7. Now substitute 6 into your function and you see what you get. We will get 5. So 8 minus 6, that's going to get us 2. So 7 minus 5 is 2. 2 divided by 2 will then get us 1. So the average velocity, or in this case the average rate of change, for that function on this time interval from 6 to 8 seconds is just 1. Let's look at the last one. So we want an average rate of change. Or in this case, again, this is your average velocity. So as we start looking at this, again, we're going to be looking at the function evaluated at 10 minus the function evaluated at 8, all divided by 10 minus 8. S of 10, when you evaluate your function at the t value of 10, we should get 13. S evaluated at 8, well, we already know that one to be 7. And this will be 10 minus 8, which is 2. So naturally what we then get here is going to be 13 minus 7. And 13 minus 7 should get us, 6. And 6 divided by 2 will then get us 3. So now the question for part B, is going to say, well, now we want to find the instantaneous velocity at t is equal to 8. So no longer looking at the velocity on a given interval, because that velocity on a given interval was just an average velocity. Now we want to just observe what is, in this particular case, the instantaneous velocity when t is equal to 8. So the velocity only at one specific value. Now, in order to do this, well, we're going to have to look at my instantaneous velocity at the given value of 8. This means that we're going to have to use the limit, and again, we can use any one of the limits that we were looking at above on the definition. We can use a difference quotient, or we can use an average rate of change for the limit. And since I'm already working with the average rate of change, I kind of want to use that. So I'm going to go with the limit as t is going to be approaching 8, and this is going to be for my function s of t minus s of 8, all divided by t minus 8. Alright, so let's keep going. This is going to be the limit as t is approaching 8. S of t, well, that's my function, that's 1/2 t squared minus 6t plus 23. And then I have my function s of 8. And remember, s of 8 we did on all those intervals. That was 7. So this is going to be minus 7, all divided by t minus 8. Okay, looking pretty good now. Let's keep going. Limit as t is approaching 8. Once again, we have 1/2 t squared minus 6t. Now we're going to have 23 minus 7. 23 minus 7 will get us 16. As such, all divided by t minus 8. Now, one of the things that I'm going to do is, since my coefficient for my t squared polynomial in the numerator is made up of a fraction, what I'm going to do is I'm going to multiply that big numerator by a factor of 2. And again, I can't just multiply the numerator. I have to multiply both numerator and denominator. So now we're left with the limit as t is approaching 8. And again, let's distribute. So distributing, we now get t squared minus 12t plus 32, all divided by 2 times t minus 8. Okay, looking pretty good now. Let's go through and let's see if we can factor that numerator. Chances are these will factor, and it's looking like it does factor. It looks like I can factor into t minus 8, and it should be t plus 4. 8 times 4 should be 32, so then when we add these two, oops, t minus 4, there we go. So then when we add these two, we get negative 12. Perfect. Divided by 2 times t minus 8. So check that out. T minus 8 factors, they simplify. And then we're left with the limit as t is approaching 8 for t minus 4 divided by 2. Awesome. Now we can do direct substitution. So making a direct substitution here, the limit as t is approaching 8, we get 8 minus 4. So 8 minus 4 divided by 2. 8 minus 4 is going to be 4, so 4 divided by 2, that's going to be 2. There we are. So what's the instantaneous velocity? Well, the instantaneous velocity in this particular case is going to be 2, and we're going to go back to the original problem, and we're now going to start taking this unit of measurement for this velocity. The unit of measurement for this velocity, since we're given feet, and since we're given t is in seconds, then the velocity here is going to be in feet per seconds. So the instantaneous velocity when t is equal to 8 for this function is 2 feet per second. Notice the average velocity on the interval from 4 to 8 was 0 feet per second. On the second interval from 6 to 8 seconds, it was 1 foot per second. And the average velocity for the last interval from 8 to 10 was 3 feet per second. So naturally, as we start looking at this, some of the instantaneous velocities are going to be better approximated for the intervals where the h value is smaller. Or in other words, where the difference in between the two interval endpoints is smallest. Because if you look at the very first one, from 4 to 8, we had a difference of 4. But on the second one, from 6 to 8, that's a difference of 2. And from 8 to 10, that's a difference of 2. And again, notice that the similarity here for the last two intervals, they were a whole lot closer to my initial, or to my instantaneous velocity at t is equal to 8, instead of the very first interval. So this is how we're working with instantaneous velocity. Now, let's see a different example. All right, so here's your question. This says that if the equation of the tangent line to the function y is equal to f of x at 4, 3 passes through the point 0, 2, find f of 4 and f prime at 4. Okay, so again, we have a few things to consider here. Okay, so what I want to do really quickly is I kind of want to draw a sketch of what they're telling me. That way I can extract just a little bit more and I can work with that. Okay, so all I'm doing is getting an axis here. Alright, here we go. So this is y and this is going to be x. Oops. So that's going to be 1, 2, 3, and 4. Okay, so the first point we're given is 4, 3. So here's my point 43. And they're telling me that the equation of the tangent line to this function y is equal to f of x at 4, 3. So at 4, 3, I know I have a tangent line. And that tangent line to the function f of x is also going to pass through the point 0, 2. So my point 0, 2, that's going to be x value of 0, y value of 2 is up here, which means the equation of the tangent line, or at least my tangent line visually, is doing this. So again, this is my tangent line. And this was my ordered pair 0, 2. So again, as you're looking at this, you can have a certain function that does this. Okay, so for your function, let's say it could have done oops, not quite that. Let's say it was looking something like this. Alright, and so it's tangent at that given point 4, 3. So again, this is just a rough depiction of what it could possibly be. So as we start looking at this, then we start extracting, okay, well, we know a lot about this function, or about this tangent line. We know that the slope of the tangent line is going to approximate the derivative of that function, or in this case, we're going to be able to find f prime at 4 by using the slope of this line. So what we then have to do in order to find the slope, or in this case f prime at 4, we just need to find the slope of the tangent line. Well, the slope of the tangent line is just y2 minus y1, so that's 3 minus 2, divided by x2 minus x1, so that's 4 minus 0, and this will get us a slope of 1/4. Okay, not too bad. So we're able to find that f prime at 4 is going to be equal to 1/4. Awesome. That's one of the questions answered. The other one says find f of 4. Well, f of 4 is not too bad because that's actually given. F of 4 is actually 3. And we're done. Just like that. Easy peasy with a little bit of lemon squeezy sprinkled in. Very nice. Now, we're going to go to the very last one. So, very last question. Here's your very last question. This says to sketch the graph of a function g for which g of 0 is equal to g of 2 is equal to g of 4, which is equal to 0. G prime at 1 is equal to g prime at 3, which is equal to 0. G prime at 0 is equal to g prime at 4, which is equal to 1. G prime at 2 is equal to negative 1. And then the limit as x is approaching 5 from the left for g of x is infinity. And the limit as x is approaching negative 1 from the right hand side for g of x is equal to negative infinity. So I want to start with a few of these descriptions. Okay, so the few descriptions that I want to start with are g of 0, g of 2, g of 4 is equal to 0. What this tells me is this is actually giving me the x-intercepts for g of x. This is telling me that at x is equal to 0, we have an x-intercept. So x is equal to 0, we have that x-intercept. At x is equal to 2, we have another x-intercept. At x is equal to 4, we have another x-intercept. So this is what the first statement is telling me. The second statement is then going to tell me that when I'm looking at g prime at 1, that this is equal to g prime at 3, which is equal to 0. This is telling me that the slope of the tangent line for g of x at x is equal to 1 and x is equal to 3 is 0. So what type of lines have a slope of 0? Well, a slope of 0 tells me that I have a horizontal line. Awesome. So we can go to x is equal to 1, and we can go to x is equal to 3, and at those given x values, we're going to have some random slope. Now, we don't know what the outputs are, so I'm just going to kind of keep this in my back pocket for now. I don't know what those outputs are. I don't know what g of 1 is, and I don't know what g of 3 is. So again, I'm keeping this in my back pocket till I can simplify some of these items. So the next one that I'm going to look at is going to be the next statement. The next statement is telling me that g prime at 0 is equal to g prime at 4, which is 1. So again, what this is telling me that the slope of the tangent line for g of x at x is equal to 0 and x is equal to 4 is 1. So in other words, I get that the slope of the tangent lines is equal to 1 at those given values. Now, those given values, well, those I know where to work at. So at x is equal to 0, I know I'm here. I'm going to have a slope of 1. So what does a slope of 1 look like? Well, a slope of 1, you go up 1 over 1. So up 1 over 1. Great. Or we could go down 1, back 1. Sorry, my dog's in here and she just got caught in the computer charger, unplugged it, and just scurried away because she got scared. Dogs are silly. Alright, so there we are. Now, at x is equal to 4, we get the same thing. So at x is equal to 4, the slope of the tangent line is going to be 1. So at x is equal to 4, again, we're going to go up 1 over 1, or we can go down 1, back 1. So at x is equal to 4, we get the slope of negative 1, tangent line, and at x is equal to 0, so at x is equal to 0, we get a slope of 1. Okay, so this should kind of tell us what the function is kind of doing so far. So I'm going to kind of just, again, keep that in my back pocket. Now, looking at g prime at 2. Alright, let's choose a different color other than red. So I'm going to be looking at g prime of 2. So g prime at 2 is equal to negative 1. Well, what does this tell me? This tells me that the slope of the tangent line for g of x at x is equal to 2 is negative 1. In other words, I get that m is negative 1, and this is at x is equal to 2. So when I go to x is equal to 2, I'm going to have a negative slope. So a negative slope, we go up and back 1, or we go down 1 over 1, and here's going to be that slope. Now again, these that I'm drawing on here dotted are slopes. They are not the function itself. So keep that in mind. These are slopes for the tangent line. And finally, at the limit as x is approaching 5 from the left-hand side, for g of x, this is going to be equal to infinity. This is going to tell me that I have a vertical asymptote. So, as the limit as x is approaching 5 from the left-hand side for g of x is equal to infinity, this tells me that I have a vertical asymptote. Okay, well, the same thing is going to happen if we're approaching negative 1 from the right-hand side for g of x. When it's going towards negative infinity, we have a vertical asymptote. Okay, that's nice. So now all I get to do is I'm going to draw those vertical asymptotes in here. So I get x at 5 here we are. I'm going to draw this vertical asymptote in here. X at -1, draw my other vertical asymptote. Anything that's dashed on my specific graph is not a part of the graph. That's why as I'm doing all of this, I'm doing it in different colors, that way to denote the different interpretations that were given. Not only that, it's also going to be a sketch. So one of the things now, I want to start going ahead and elaborating more on this and actually depicting the graph. So now what I'm going to do is I'm going to start using all of these guidelines in order to generate my graph. So I know as x is approaching -1 from the right hand side, it's going down towards -infinity, which means I'm going to be coming down this way. Okay, now as my function is approaching x is equal to 0 and it gets to x is equal to 0, not only is it going to cross, but it's also going to give me a slope of 1. Notice that's the slope of the tangent line that I drew there. Coming back down to this point of x is equal to 2, I know that that's an intercept, but as we keep coming downward, we also know that the slope of the tangent line at x is equal to 2 is going to be -1. And then finally, as x is approaching 4, we know that the slope of that tangent line should be approaching 1. So that means it's going to turn back around. Now, I haven't used these values yet. At x is equal to 1, what do we know the slope of the line to be? It's horizontal, which means we have a horizontal slope. Great. And so as I'm coming here to go over to 4, I'm going to keep going, turn around there. Slope of the tangent line is 1. Okay, and again, at x is equal to 3, notice I have another horizontal slope. And my function now is going to be approaching 5 from the left-hand side, and that goes towards infinity. So here is a possible sketch for my g of x. Notice all of these extractions. Limits in this particular case are giving us an insight into these asymptotes. Awesome. Doesn't necessarily need to give us asymptotes. It could give us some, let's say, discontinuities or some values that we're approaching for those limits. The derivatives, though, they give us more of an insight as to what the function is doing at the given points that they're elaborating on. So the slopes of the tangent lines, or as we'll call them, the derivatives, they're going to give us insight into the shape of the graph. And that's what we want to keep in mind. So I hope you all enjoyed this lesson. We're now done with this particular section. And stick around and we're going to go over the next section where we'll be talking about the derivative of a function. So we're going to formalize this a little bit more, and we're actually going to give it a name, which will be the derivative. So if you want to stick around for that, we'll be back in just a bit.